Hi, welcome to one more video on stability analysis using Nyquist plot. In this video, we'll see a transfer function which has got a pole on either side of the S-plane, that is on the right hand side as well as on the left hand side of the S-plane. So we have it at -4 and 1. Since this pole is enclosed by this Nyquist contour, so that's why the P is becoming 1 now. So let us try to map the different segments of Nyquist contour from S-plane to GH plane. So if you can consider this particular transfer function, the magnitude, that is the transfer function, what we have is 20 by S plus 4 into S minus 1. The magnitude equation happens to be this, whereas the phase equation is, you can see there is a -1 term. So this -1 term has to be carefully taken care, and then we have to write it as 180 minus tan inverse of omega by 1. So this reduces the phase to -180 degree minus of tan inverse of omega by 4 plus tan inverse of omega. So with this magnitude and the phase equations, for different values of omega, you can find out what is the magnitude in the phase. So as it was discussed in the earlier videos also, when you have a plus and minus term, it is customary to not to just give only the extreme values. So just give one intermediate value that is very close to 0. Give it as 0.1 so that you can know, since the initial phase and final phase are both are -180 degree, in order to know whether the phase goes less than -180 or more than -180, so we have given omega as 0.1. Actually the phase has become -175, so and then it goes to -149, and then finally as the value of omega goes to infinity, the magnitude reaches 0 and the phase is still again -180 degree. So meaning with the magnitude of 5, so it is going down here. You can see this is -180, this is -175. It is going down and then again it goes back to -180 degree. So this is segment 1 mapping onto GH plane. We know that the segment 2 is still a dot at the origin. Segment 3 happens to be the mirror image of this. You can see mirror image of this is over here. If you actually put the direction of these contours going from 5 to 0 origin and then back to 5, so this is the direction, the rotation of contour on GH plane. You can see since the magnitude is 5 here, so -1 plus j0 actually comes inside this. If you actually see, this is actually encircled by contour in anti-clockwise direction, so that's why the value of n is equal to -1. Since p was already 1, so why p is 1 means, okay, since there is one pole, this is open loop pole enclosed by the contour because of this s minus 1 term, so that's why p is equal to 1 here. So p is 1, n is actually -1, so this comes out to be z equal to 0. So this z equal to 0 actually corresponds to the closed loop system is actually stable in nature now. You may wonder that, okay, since even though you have a pole on the right hand side, so and of course you have a pole on the left hand side, as the value of k is 20, that is when the gain is 20, this actual pole will actually come to the left hand side over here. So that's why the value of z is becoming 0 here. So z is 0 because for this value of 20, the poles, all the poles are there onto the left hand side of the spline. That's why the system is stable. So this way, even with the value of p is non-zero, so that's what the definition says. So definition was said that if the value of n is equal to non-zero, if the system to be stable, we need to have the number of encirclement of -1 plus j0 should be as many times as the value of p in anti-clockwise direction. You can see that's why it is happening in anti-clockwise direction once. So meaning that n plus p will become 0, system will be stable. We'll move on to next plot. Here you can see we have transfer function which is over here given as one pole at the origin, and we have two poles on the left hand side. Since you have a pole at the origin, so we will go to of course the contour should be such that it should cover the entire right hand side, but it should not go through, it should not pass through any pole or 0. So that's why it is not passing through this pole at the origin, but this is now bypassed by one more segment. This segment is the fourth segment. We'll discuss about this fourth segment when we start mapping this particular segment onto GH plane. So this is in a S plane. We know that first segment is j omega, second segment is r e power j theta, third segment is minus j omega, the fourth segment is rho e power j phi. So we'll just see that. So this is the first segment mapping. So as usually we substitute S as j omega, we find the magnitude and the phases. So this is phase when omega is equal to 0, it is 90 degree to minus 270, magnitude varying from infinity to 0. So since it is going through minus 90 to minus 270 degree, so this will certainly pass through minus 180. So that frequency happens to be 6.32 radian per second. So the magnitude at that frequency happens to be 0.071. This is the second segment, is still a dot at the origin. This is what is a fourth segment mapping. So as I said, fourth segment S is equal to rho e power j phi, where rho is tending to 0. Phi is actually varying from minus 90 degree, 0, and this is actually plus 90 degree. So pardon me for that, this is actually plus 90 degree. So let me just change that. Because please consider this as plus 90 degree here. So this has been made here properly. This is minus 5 means okay, this is so and so. You can see now we are trying to map this fourth segment, which is this small portion whose radius is tending towards 0. The phase angle actually starts from minus 90 degree, 0, and plus 90 degree. So that's what is minus 90 degree, 0, and plus 90 degree. And this rho is tending to 0 because I'm not supposed to uncover any portion on the right hand side. That's why I'm just making this magnitude 0, and it is not passing through this also because it should not pass through any pole or 0 at the origin. So upon looking into all these things, segment 4 on the GH plane happens to be with a magnitude infinity, and it starts with a phase of plus 90 degree, 0 degree, and minus 90 degree. That's what is this mapping of 4 segment corresponds to. It is infinity at an angle of minus phi. Since phi is varying from minus 90, 0, plus 90, so this happens to be 90 degree, 0, and minus 90. This is what is minus phi is. So let us see how does the entire plot looks like. Okay, this is only the first segment mapping, because first segment goes from minus 90 degree with magnitude infinity up to minus 270 degree with magnitude as 0, and when it is minus 180 degree, you can see the magnitude is 0.071. So this is the first segment mapping for this particular transfer function. The second segment is a dot at the origin. The third segment is actually the mirror image of the first segment. The overall transfer function, overall Nyquist plot looks like this. This is the first one, this is the second one dot, third one is the mirror image, the fourth one starts with the magnitude of this actually plus infinity, sorry for that. So this is infinite with phase as plus 90 degree. Let me change that. Of course, this is the fourth segment is starting with the magnitude of infinity, and phase is plus 90 degree. It goes down to 0 degree with again the magnitude as infinity. So still minus infinity with angle of minus 90 degree. That's what we saw in the mapping of fourth segment. You can just have a look at it here. The fourth segment is infinite 90 degree, 0 degree, minus 90 degree. That's what exactly here. It is, you can see infinite 90 degree, this is infinite 0 degree, this is infinite minus 90 degree. So it's like the contour should go with like a relay running. So it is starting with infinity with minus 90 degree, it goes till the origin at minus 270 degree. From here it is at the dot only, then it is the mirror image, it just goes there till infinity at an angle plus 90 degree, and then it completes the path. So contour is 1, it should have a closed path. Now you can that. So you can see today is 0.071. So minus 1 plus j0 actually is coming out of this particular point, meaning this entire Nyquist contour never encircled this minus 1 plus j0. So that's why n is equal to 0. And since the transfer function has got all the poles to the left hand side, even there on the origin, so since nothing is there on the right hand side, that's why p is equal to 0, and z value happens to be 0, so that closed loop system is stable in this case. We'll see one more transfer function, which is now 200 by s square plus s plus 1. We have two poles at the origin. You can see there are two poles at the origin. This also is a special Nyquist counter with 4 segments, 1, 2, 3, 4. So segment 1, again replace s by j omega, find the magnitudes and phase, which is minus 180 degree to minus 270 degree. Then see the second segment, s is equal to r e power j theta. So it will end up with a dot at the origin. You can see 0 magnitude, whatever the phase, it will be a dot. The fourth segment will be slightly different. You can see rho e power j phi, where rho is 0 and phi is varying from minus 90 degree to 0 degree plus 90 degree. And upon substituting this s is equal to rho e power j phi to this transfer function, we end up with this as 20 rho square e power j2 phi into so and so. Out of these, 1 plus rho e power j phi, as rho tends to 0, this is negligible compared to 1. So this entire term is neglected. You end up with only 200 by rho square into e power j2 phi. So naturally, when rho tends to 0, so this entire magnitude becomes infinite. That's what you have, infinite. And the phase is here in the denominator is 2 phi, so this becomes minus 2 phi. Since we know that phi is ranging from minus 90, 0, plus 90, so this will become 180 degree, 0 and minus 180 degree. So here there will be ambiguity whether to have it as, because 180 degree to 0 degree, you can go from the second quadrant to first quadrant, or from third quadrant to fourth quadrant. So instead of having any ambiguity, so that ambiguity can be removed by splitting this phi from minus 90 to 0. You can write it as minus 90, minus 45 and then 0. From 0 to 90 degree, you can write it as 0, plus 45 and plus 90. So then splitting that entire angle from minus 90 to plus 90 like this, we will have the angles as plus 180 degree, plus 135 degree, 0 degree, minus 135 degree and minus 180 degree. Here there is no ambiguity. From 180 degree to 0, it will actually go in the second quadrant and the first quadrant. Here we had ambiguity whether to go in the second and first quadrant or third and the fourth quadrant. Now it is very clear that it is infinite in the second quadrant, and then it moves to 0 through second and the first quadrant. So let us see how does the overall plot looks like. This is what the plot is. So we started with infinite magnitude at an angle of minus 180 degree. It just went up here, and then it's again at, you can see, this is at minus 270 degree, the first segment. This is from minus 180 to minus 270. You can see this is minus 180 to minus 270. Here the angle, this is minus 3, this is 270 degree. That's why it is moved to second quadrant, and then the second segment is a representation by a dot. The third segment is the mirror image of that. It comes to infinite at an angle minus 180 degree, minus a plus, because minus 180 is exactly equal to plus 180 degree. Later afterwards, it moves with plus 180 degree, and then it goes to plus 135, then it goes to 0 degree, then it goes to minus 135, and then finally it goes to minus 180. That's what is this we had. You might have seen that in the previous slide. It went like that. It is plus 180, plus 135, 0, minus 135, minus 180. This is exactly that entire trace. So this is that entire trace. Looking at this, if you see the value of n, it is plus 1 here. So actually n is equal to 2. P was actually 0. So z is become to be 2. So system is actually unstable, because you have a repeated poles at the origin. So as soon as the value of k goes above 0, the system will become unstable, because two poles come onto the right hand side of the S-plane. Two closed loop poles come onto the right hand side of the S-plane. So this way we can say system is unstable in this case.